In this video, we're going to be going over the base on which all of chemistry is built, and that is the atom. We're going to be breaking down the atom into its various sub-classifications: the element, the ion, the isotope, as well as its subparts, what it's made of. And then we're going to move into some notation, some standard notation that you'll see throughout your chemistry course. So hopefully by the end of this, you'll have a better feel for all of those things as you move into chemistry. So starting out, what is the atom? The atom is the most fundamental building block of matter. If you're thinking about some molecule, typically you're going to think of it as its subatoms. You're going to think what atoms are in this molecule. For example, you might think of simple sugar, some glucose, and you're going to think of that as C6H12O6. The C, H, and O are all different types of atoms, and they come together to build your they're going to come together to build your glucose. They're going to come together to build your molecule. And you're going to think of that molecule in terms of its subatoms. So, what are atoms made out of? Atoms themselves are made of smaller things. They are made of protons, neutrons, and electrons. The protons are large, positively charged, and they reside in the nucleus in the middle. The neutrons are large, neutral, so they have no charge, and they're also in the nucleus. Finally, you have the electrons. They're small, they're negatively charged, and they are going to be in the outskirts. So let's maybe just draw ourselves a diagram of a simple atom. A simple atom might look something like this. You have your proton, your neutron, and then floating around here, you have your electron, and it's just moving its thing, zigzagging around. When you first learn chemistry, you might learn that it just orbits like a star orbits, or like a planet orbits a star. But actually, its movement pattern is much more complicated than that. But we'll get into that later. For now, just think about it as if it's orbiting. Important note, there's a few important notes. The electron and the proton perfectly cancel. It's not like the electron is half as negative as the proton is positive. They perfectly cancel. So if you have one electron and one proton, the net charge of your atom is going to be 0. Another important thing is that the ground state of an atom is going to be so that this number equals 0. Usually, atoms don't like to have, 5 protons and 1 electron, where its net charge would be +4. They don't like that. They want their net charge to be 0. So typically, that's how they're going to be found. So now that we have a little bit down about the atom, let's move into the element. What's an element? Elements are the types of atoms. An atom can take specific forms, and those forms are largely, in their broadest form, broken down into distinct elements. An element is determined by the number of protons. If you have one proton, you are of the element hydrogen. Two protons, helium. Three protons, you're going to be lithium, and the list goes on. So all an element is an atom of a specific number of protons. That's all the element is referring to. Now there are going to be 118 elements because once you start getting real big, the protons, they really don't like being around each other and they're going to try to get away from each other. So once you are more than 118, you can't exist. And at 118, you only exist for extremely short periods of time. So there are 118 elements, and we'll learn more about how those elements behave a little bit later. Now we just saw if a proton number changes, different element. What if the neutron number change? What if this one changes? If that changes, we get into our next categorization, which is the isotope. A given element can have multiple different isotopes because the same number of protons can be in a nucleus with differing numbers of neutrons. Maybe you have one proton, one neutron, so hydrogen, and that would be the hydrogen 2 isotope. Or you could have just one proton with no neutrons. That would just be the hydrogen 1 isotope. Or maybe you'll have a proton and two neutrons, and that would be the hydrogen 3 isotope. So all the isotope is if you have an element, what if the neutrons are different? What if you have a different number of neutrons? Finally, we get into the last. So we just talked about the atom, the element, the isotope. Now what about the ion? What's an ion? This is when instead of the neutrons changing and instead of the protons changing, the electrons change. So if you have a proton, it in its ground state, as we discussed, is going to just have one electron floating around. But sometimes, under certain circumstances, if there's something real strong pulling at this electron, just yanking at it, and this electron decides to pop off and go over here, well, now there's not going to be an electron. There's just going to be the proton. So this is going to have a net charge of +1. So this hydrogen is a little bit different than it was before. So how do we describe that difference? Well, we call this an ion of hydrogen or ionic hydrogen. And all the ion means is that it lost or gained an electron. Sometimes you'll have an element, hydrogen doesn't do this, but other ones do, where let's just draw this nucleus, and it likes having, let's say it has 7, and this makes it neutral. Sometimes an extra one might plop in because maybe it's floating around, or maybe something didn't really want it, so it gave it away. And now this is going to be negative. This will also be an ion. So if you have an element that gains or loses electrons, that element is now an ion. If it lost electrons, it will be positive because now it has more protons than electrons. And that is called a cation. And then if it is negative, that means there are less protons than electrons. And that means it is an anion. The only way to become an anion, importantly, is to gain electrons. Because you might think, oh, you could also become negative by losing protons. But remember, if you lose a proton, you're going to turn into a different atom because, sorry, different element. Because remember, element is defined by the number of protons. So if you have a different number of protons, you're not the same element anymore. So you won't be an ion of that element. You'll be a different element. So that is just a brief introduction to the ion, the element, the isotope, and the atom. Now let's go over a little bit of notation just to make this all very standardized. Generally, when we write out an element, we're going to write it this way. We'll have a symbol for that element. So, for example, hydrogen is an H, helium is an He, oxygen is an O. So we'll have that symbol. And then right here in the bottom left, you're going to have Z, and that is called sorry, the atomic number. The atomic number refers to how many protons. So let's say you didn't know, you weren't familiar with the symbol. The symbol is going to be dependent on the number of protons because the number of proton defines the element, and the symbol is just the symbol of that element. But if you don't know how many protons this element or that has, you can see it right here. It'll be right here in the bottom left. The next important thing is up here. The A is called the mass number. This would help you determine, okay, what isotope am I looking at? Because remember, for example, hydrogen, let me just rewrite this, XCA. Remember, hydrogen could be hydrogen 1, hydrogen 2, or hydrogen 3, where this 1 refers to the fact that there's just one proton. This 2 refers to the fact that there's one proton and one neutron. And this 3 refers to the fact that there's a proton and two neutrons. This A will give you that. This will tell you how many protons are there plus how many neutrons are there. So you can figure out how many neutrons there are by taking A minus Z, because A will be protons plus neutrons and Z will be protons. So that should equal neutrons. So the last important thing in our standard notation here is going to be the charge. Now, a lot of times you will only see this. Q, sometimes you put it in there, sometimes you don't. So I would definitely know this, but I think this is good also to know, just to be familiar with the fact that it exists, and you will be using it much more later on. So the Q up here is going to tell you the ion, because the Q is the charge. So if it is positive, then you have a cation, and if it's negative, you have an anion. So a few examples might be oxygen, you might see as oxygen, and in this case, you know, okay, just an element here, and make it complete, right? The 8 and the 16. So this is the ground state element where you have 8 protons and 8 neutrons. So 8 plus 8 makes 16. But you also might see O2 minus. And you're like, okay, what does O2 minus mean? Well, O2 minus is going to be the ionic form of oxygen. And all this is telling you is this specific oxygen has grabbed 2 electrons, and in doing so, become an ion. So it is the ionic form of oxygen. The last important note is atomic mass versus mass number. So when you see an element, many times you'll see it written as such. Where you have a number down here, I just made up a random number, and then you have your atomic number up here. And you're like, what number is this? What am I looking at down here? It's not mass number, and you might be able to tell pretty quickly that it's not, because it'll be some weird decimal to be like 12.5. You're like, I know a mass number is not going to be 12.5. It is actually the atomic mass. That's what you're looking at down there. So what's the atomic mass? The atomic mass is just the weighted average of all the different isotopes. So for example, let's say that I had 90% in nature of all hydrogen is in hydrogen 1, and that 10% of all hydrogen is in hydrogen 2. And this is just an example. The atomic mass for hydrogen under this example would be 0.9 times 1, because 90% of it is 1, plus 0.1 times 2, because 10% of it has a weight of 2. So this would be 0.9 plus 0.2 equals 1.1. So in this instance, my atomic mass of hydrogen would be 1.1 because I went out and I found that 90% of my hydrogen had a weight of 1 and 10% had a weight of 2. So I took the weighted average of those weights to get my atomic mass. And that's what atomic mass is. Oftentimes you'll see it written as average atomic mass. So that really just drills in that it is an average. So the last important thing to talk about is the atomic mass unit. The atomic mass unit, often called U. So the atomic mass unit is how much 1/12 of a carbon 12 atom weighs. So if we think about it, if a carbon 12 atom has 12 total protons plus neutrons, that's what this 12 is referring to. You might be tempted to think, okay, any given proton or any given neutron is going to have the weight of 1 AMU. And you might be tempted to think that that's a reasonable thing to think, but it isn't true. And that is because of the mass defect. So we're going to go over that briefly. And that's why you might see that hydrogen 1, so just to throw out an example, this might not be true. So let's do a different one. Helium 2. Instead of having a 2, it might have like a, I don't know, 1.9999 or something. I don't know. That's just an example, but let's see why that could be the case. And you will see decimals like that that are just like, what's that decimal doing there? We're going to explain that here. So here's an equation that everybody knows and nobody understands, right? E equals mc squared. Your grandma probably knows about this equation, but in our instance, we're actually going to use this. This says that energy and mass are linearly related. The c squared is the speed of light squared. So that's just a constant. So E, energy, and mass are linearly related. That means that they are talking about the same underlying thing. If I say energy and I say mass, I'm talking about the same underlying thing. So what does that mean in concrete terms? It actually means that if I chuck a ball across the room, when I was holding it in my hand, it actually weighed less than now that it's hurling across the room compared to me. Compared to itself, just when it's sitting here chilling to itself, it weighs the same as it did before. But compared to me, now it weighs more. So that might have been a little bit complicated. Just know energy and mass, they're related. They're actually saying the same thing. So if you have more energy, if you're something that has more energy, you're actually going to weigh more than if you were that very same thing, but you lost a little bit of energy. So what does that have to do with the proton and the neutron? Proton and the neutron. Well, if you remember, protons are both positive. And we know that positive things repel. They don't like being near each other. So, how on earth do they stay inside the nucleus? How do they not just zip apart, explode right on the spot? That is because of a different force. So, positive repel because of the electrostatic force. Electrostatic force. But there's another force holding them together, and it's why the nucleus doesn't just explode. And that is the nuclear force, the strong nuclear force. So, what does the nuclear force look like? The nuclear force is just going to hold any nucleon together. So, if you have this neutron here, it's going to impart a strong nuclear force on a proton or another neutron. And it's just going to bring them together. And they're just going to be real happy now that they can be close to one another. They're happier that way than they were when they were apart. So, what does this have to do with atomic mass unit? What does this have to do with mass? And why would mass be different than I would expect? Well, when that strong nuclear force is being enacted on two different protons, let's say, so let's say proton A and proton B, they're just chilling, doing their own thing. Once that strong nuclear force makes them come together, boom, now they're together, right? At this point, they have less energy than they did when they were apart. Why might that be? Well, think about it. If we potential energy U is broadly defined as the ability to do work. If you have this proton here and this proton here, and they're far apart, they have the ability to come closer together. But now that they're closer together, they're stuck there. They have the ability to do nothing except stay there. So when they were here, they had higher potential energy than now that they're here. Now they're at lower potential energy. They lost energy. So if they lost energy, just like we said before, they also lost mass. They weigh less now that they're together. They were heavier when they're apart. Now they are lighter. So that is an important note. Free protons weigh less, or sorry, weigh more than um, bound protons. So that is the very important thing to take away from this. And that is why U doesn't just equal protons or neutrons. It only does in the context of carbon 12. So there's one more kind of cool, I don't know how important this will be for you, but it's cool to know about the mass defect. And that is that it has a tendency to saturate. What do I mean by that? Well, the strong nuclear force has a limited range. So if you have this proton here, it's only going to impart a strong nuclear force in this limited range here. That opposed to like gravitation or the electrostatic force, which is infinite, it'll impart, albeit small, a force on something way over here, not the nuclear force. The nuclear force is confined to this or confined to this little area here. So if you have this proton over here, it's not going to feel a thing from the strong nuclear force over here. Not a thing. It's only going to feel something when it's close enough. So now that it's here, boom, now they're going to come together and they're going to form this little dyad. So what does this have to do with anything? Well, let's think about it. If I have one proton and another proton, they're going to have lost a little bit of energy now that they're in this configuration. But do you think it's going to be harder or easier for me to pry these two apart than if I plopped another one in here? If I plopped another one in here, now this one's going to be enacting forces on this one, which will be enacting on this one and this one. And this one will also be on this one on this one. There's going to be more forces pulling them together, making them scrunch up in a tiny little ball than if there were just two. So these actually have more energy than these. Now that they're scrunched together like that, these actually have less energy than before. So not only does a free proton have more energy and thus more mass than two protons bound have more energy and just more mass than three bound. And you might think, okay, does that just go all the way up? So now that if I have three, four, and I just have a huge nucleus like this, does that mean that this will, at a certain point, once I get big enough, just weigh nothing? Will it just weigh 0 grams? Well, that is where the limit of the range comes into play. So once you fill up this range, and it's all full of protons, if you add another proton here, it's not actually going to be interacting with the entirety of this range. It'll only be interacting with a set amount. So there is a max that you are able to interact with. And the thing is, though, like we said before, this electrostatic force, these protons over here, they're still going to be repelling this proton. Because even though the nuclear force doesn't reach, the electrostatic reaches on for infinity. So now it's going to have the same amount of nuclear force. Every added one is only going to get that same bonus, but it's going to have that electrostatic force pushing against it. And every time you add another one, it's going to be even more electrostatic pushing against you and more electrostatic pushing against you. So that's actually going to add energy because now it's a little bit easier to pry that apart. It has a little bit more potential energy. So since it has more energy, it's going to weigh a little bit more than you would have expected otherwise, than you would have expected if the trend continued. So now at this point, you might be wondering, okay, so what is the lowest mass per nucleon? Like, what element is it so that I am minimizing my energy? I have the lowest number or lowest amount of energy possible. That's actually going to be iron 56. So iron 56 is actually going to be the point where your atom is just in that sweet spot so that the electrostatic force felt by all of those protons is the best accommodated by the nuclear force. So this brings us into a minor note that isn't really important, but I think it's really cool, and you might see it. This brings us into how atomic bombs work. How do atomic bombs work? And atomic energy more generally. So you might be told, you might have heard that fusion gives energy and that fission, spelled fission wrong, and that fission gives energy. And if you know, fission is the splitting apart and fusion is the putting together. So if I split apart an atom and I get energy, and then I put an atom together, I get energy. Where is the energy coming from? Why can't I just split an atom apart and then put it together again, and then split an atom back apart, put it together again? Infinite energy, right? That is where what we just learned about the strong nuclear force comes into play. So if you are smaller than iron, we saw how every extra, so let's say your oxygen, every extra proton you add makes all of the protons, including this one, weigh less. Every proton you add adds stability. It makes this more stable. It makes everything weigh less. It lowers the potential energy, and in doing so, it releases that energy. On the other hand, once you're really, really big, we saw how once you're really big, you're past that point of iron, you're huge. Every time you add another proton, it actually makes everything heavier. It makes everything less stable. It lowers or it raises, sorry, the potential energy of everything in that atom because now you haven't added anything extra to your nuclear force because nuclear force is saturated, but you have added something to the electrostatic repulsion. So instead, every time you take a proton off of this atom, you get energy out. Because now, if you take a proton off, this leaves, and now it's over here. All of these in here, now they weigh less. They weigh less because now they have less of that energy that was being given to them by the electrostatic repulsion. So now that they weigh less, they actually gave off that energy. They gave it off. So fission only works if you're bigger than iron. And then fusion only works if you're smaller than iron. So if you tried to fuse helium with another helium atom, yeah, you would get energy. But if you tried to do fission on helium and turn helium into two hydrogens, you would have to use energy to do that because the hydrogens both have more energy than the helium does. So the helium and these hydrogens, these protons are of higher energy than these protons are. So they had to be given energy. But conversely, if you go the other way around, going from here to here, you're going from high energy to low energy. So you're going to give that energy off. So that is how you're going to give or get energy using the atom.